Welcome back. This is Larry Benko, W0QE. In this video is about the reference or measurement plane. All users of VNAs or network analyzers, whether they are large expensive types or modestly priced hobbyist types, should be aware of the reference plane. Ignoring the reference plane will result in measurements that are less accurate than your VNA is capable of. Shown here in this drawing is what a typical VNA calibration might look like. We have a VNA with a particular connector type on it, which is determined by your VNA. It may not be compatible with what you typically like to use, so you may need an adapter here, which converts from this connector type to this connector type. A piece of transmission line, typically short, to get to the device we're going to ultimately measure. And we may have another adapter because the connector types that we have on our open short load may not match the connector type in our cable, or may not match the connector type on the device we wish to test. So this is a typical type of a setup. And when we're done, the VNA is calibrated at this reference plane right here. However, this reference plane is not at an interface you'll ever be able to use, because when you remove the open short loads, you're left with either a boundary right here, or if you remove the adapter, you're left with a boundary right here. One of these two is going to be where you desire the reference plane to be. However, the reference plane from the point of view of the VNA is out here. So what are we going to do about that? So here I've taken the original drawing I had and expanded upon it somewhat. I'm assuming the problem is as follows. I have a device that I want to make a measurement on. The device is specified to have an input impedance right here of 100 plus J0 at 100 megahertz. It's got a connector type on it that mates directly with this connector right here. So once I remove my calibration stuff, I can just put the device under test right here and make a measurement. However, my open short load does not have the same connector type as the device under test, so I needed an adapter here to go from this connector type to the connector type here. I'm going to assume for a moment that there's a 1-inch disparity between where I want to ultimately make my measurement, which is right here, and where the reference plane is. If we have 100 ohms after we calibrate at this desired measurement plane, that means we had 98 plus J11 back here at the mythical reference plane, which means the VNA will read 98 plus J11. You can think about this a little bit differently. Think of there being a real load out here that's 98 plus J11. We've got 1 inch of transmission line. That gives us rotation to 100 plus J0. This transmission line is assumed to be 50 ohm Teflon type dielectric. And this 100 ohm is the desired measurement plane. The VNA gives us the wrong answer. However, VNA manufacturers have realized that people don't always make measurements at the reference plane. The reference plane is the most accurate place to make the measurement. Any place else will have small errors that will creep in, but you can't always make it there. Here's an example where I can't make the measurement where I want to make it. So what am I supposed to do? If your VNA software is able to do something called line extension, what you do is you set the VNA up to do line extension. In this case, this VNA would be set up to do 1 inch minus 1 inch of line extension. So instead of extending the reference plane out this way, we're going to bring it back 1 inch. Now, based on your VNA and then the software in your VNA, that line extension may be assumed to always be 50 ohm transmission line. It may allow you to set the impedance of the transmission line. But in a case like this, if this is a 50 ohm open short load structure and here's this built in a 50 ohm cable, this adapter may be a cheap adapter. If you bought a cheap adapter, it could easily have the wrong kind of plastic in it, which is what you typically get for $2 and $3 adapters. And they will have a lower impedance than 50 ohms. This lower impedance means that I have two different types of transmission line in here, but I can only put typically one type in for my line extension. You would have to average those impedances out, and again, you would have a little bit of an error. I would suggest that you put a decent quality adapter here that's 50 ohms. I would suggest that your open short load be 50 ohm structure too, and then you can just take care of this in one fell swoop. So 1 inch line extension with a 0.695 velocity factor, and you're good to go. Now, I have moved, as far as the VNA is concerned, I've moved the reference plane back to here. So now when I put my device under test, plug it into my network analyzer, my network analyzer reads 100 plus J0. Now what do you do if your analyzer does not allow you to do that? My big analyzer does not allow me to set inches of line extension, but it does allow me to set picoseconds of reference plane movement. So I have to sit with a calculator and calculate how many picoseconds 1 inch is at a 0.695 velocity factor, and I'm good to go. My little analyzers allow me to set the line extension based on any impedance transmission line here, but it has to be a constant impedance throughout this length. What if we don't want to do that and we want to actually calibrate for something here? We have a crummy adapter here that's got maybe a 40 ohm impedance. And the reason that the crummy adapters have lower impedance is that the dielectric constant of the plastic they use is higher, and the impedance in a transmission line is proportional to 1 over the square root of the dielectric constant. So if we increase the dielectric constant by 1.5, then we decrease the impedance of the transmission line impedance of the adapter by 1 over the square root of 1.5. SimSmith can do this for us. If we bring out from our VNA the wrong answer, we just run the calibration. We don't do anything with line extension. We just put the device under test here. We measure it, and we'll get 98 plus J11. If we take the file that we can take out of our VNA, put it into SimSmith, we'll have something like this. 98 plus J11 will be the input. That will be a file normally, but I just put the data point in here for the moment. 100 megahertz and a transmission line of 1 inch, 0.695 velocity factor, which is Teflon, 50 ohm, and I can see what happens. I'm at 99.7, close enough to 100. And SimSmith will do that for us. SimSmith can also have 2 different pieces of transmission line in here, so that if my adapter was different impedance than my open short load, I can compensate for it in SimSmith. But I can do it in SimSmith, or I can do it in my network analyzer itself. But I do need to make the change here. The difference between 98 plus J11 and 100 plus J0 may or may not be significant to you, but as the frequency goes up, these errors will get larger. As the length of this difference that I need to adjust gets larger, my errors will go up. So it's something to keep in mind. I suspect most people do the open short load and don't recorrect. Even if you don't need an adapter, you do the calibration, you get a reference plane here. I don't think most people take into account the distance between here and here. And if your if your open short loads are small, like SMA type loads, that's a smaller distance. That helps you, as opposed to an in load or a BNC or a UHF type open short load. But nevertheless, all of them need to be adjusted. And if you don't adjust it, you're just throwing away accuracy in your VNA. Before we move on, I'd like to discuss some warnings. The VNA line extension, in my opinion, should be done through a constant impedance. That makes life simpler. It may also be the only way to do it with the VNA software that you have. But if the adapter has a different impedance than the open short load, it just forces you to have a level of complexity that probably isn't worth it, and it's probably worth trying to find a better quality adapter somewhere. You can find them on eBay. You can just buy one outright, but it's going to cost you more money than you might want. I mean, $25 or $35 is not unreasonable for an adapter that's a quality adapter. But nevertheless, that does save you the problem of having to guess at an impedance for these two if they're different. VNA calibration frequencies and scan frequencies is a constant source of problem for people. You calibrate over a range of frequencies that you think is adequate, but then you scan later on at some incredibly small range of frequencies, and the VNA is responsible for doing some interpolation between the frequencies. If the VNA was calibrated at, say, 9 megahertz and then 10 megahertz were the 2 points, and you're using it at 9.5, the VNA needs to interpolate the 9 megahertz value and the 10 megahertz value to get 9.5. How it does that is a function of the VNA software. You could do it with some kind of curve fit, which would be good. It typically probably does it as a straight line fit. I know how my analyzers work, but it's something to keep in mind. And the only thing you can do is change, when you get something you think might be a little bit incorrect, is to increase the number of calibration frequencies. It takes longer to calibrate. It generally doesn't hurt you to have more calibration frequencies because it's just in software. But the other thing to keep in mind is whenever you're doing the calibration, averaging. A lot of analyzers do a lot better job if you average. So instead of taking a calibration point once, you make 10 measurements and average those for the calibration point. And then when you scan it, you take 10 measurements and average that number. That gets rid of some of the noise in the analyzer, which again is another way to improve your measurement accuracy without buying a more expensive analyzer. This is a warning, and everyone should be aware of this, but the analyzer puts out power. This analyzer puts out power to make this measurement. And if you have a very sensitive circuit out here, you could hurt that circuit. Different analyzers put out different power. My 4170 puts out minus 18 dBm. My 2180 puts out plus 6, but although it's adjustable, this is the typical range for most VNAs. As you get to plus 10 dBm, you can do damage to a radio if something was connected directly to it. Be careful. If you do that, you have to put an attenuator in this circuit. If you put an attenuator in this circuit, it will reduce your accuracy. But again, you do what you have to do, and just be aware of what the limitations are. This slide shows a lot of different connectors, and all of them are open short loads of various types. These are some very expensive precision open short loads. This is a little test fixture I've built that has open short load capability on it. Use some SMA open short loads, some BNC female, BNC male. This is a BNC to banana, and then underneath it here is a short and a load. An in female, in male. You can build these yourself pretty easily. I could do a video on these and some measurement accuracies if somebody would like. What I typically use to connect to odd components is something which has some little clips on it a lot of times. And that obviously begs of some kind of line extension again. In this case, I have these particular BNC male adapters where the reference plane is marked with this black line, and that is the offset for this adapter. Turns out to be exactly the same offset as from here to here. These are the same kind of BNC connectors. These just happen to be silver plated, and they're compression type connectors, so I could take these apart and put the open short load in there easily. These are meant to be crimped on a connector. I just cut off the crimp piece and put the wire through the center to the pin. They have the exact same reference point. So here, if I use this calibration set to calibrate my VNA, and then I put this into my VNA instead of these, I have no offset needed. The reference plane is right there. Now I do need to do line extension for the length of these leads, but I don't need to do any other compensation. And here I'm going to do a little example showing how this works exactly. Here's the 3 open short loads that I used to calibrate. They gave a reference plane that was right here, and on this reference plane is a silver mica capacitor of 910 picofarads soldered on. And let's look at what we get. I'm going to scan the circuit shown in the picture there with a 4170, and here's what we get. Well, we notice to begin with, the capacitor appears to be resonant at about 24.7 megahertz. Above 24.7 megahertz, it's inductive. Doesn't look like a very good capacitor. If we measure the capacitance down here at low frequencies, we see it around 900 picofarads, which is what we would expect. We see at 10 megahertz, we see the value being 1,078 picofarads. So this begs the question, is there something wrong with my analyzer? Something wrong with my calibration? Something wrong with my test setup? Or I just don't understand what's going on? Well, the answer to that's pretty clear. And what's going on, at the very least, is the fact that we did not compensate for these leads. Now you might think that these leads are not that big of a deal. They represent a little bit more than 1.4 inches, like 1.42 inches or 3.6 centimeters. The wire diameter is 0.025 inches, and the center-to-center lead spacing is 0.25 inches. If we put that into one of the little calculators that's available for open wire line, we come up with open wire line that has a surge impedance of 360 ohms. So we could have put that into the 4170. I could go over here to line extension, and I could say add a line extension of 3.6 centimeters with a impedance of 360 ohms and a velocity factor of about 0.95 since it's air dielectric. And I can rescan this. I'll leave this scan on the chart, and I'll rescan it. And what we're seeing now is something that's a lot better. Before it went inductive at 24 megahertz. Now it appears to asymptotically approach zero, which is what you would expect a capacitor to do as it goes up high in frequency. The effective capacitance we see is around 900 picofarads. At 10 megahertz, it's still 903 picofarads. So it's a much better circuit. This is more attuned to what the capacitor really looks like. Now this is a case where this small amount of wire that you might think is inconsequential had a huge effect. You would draw the conclusion that this capacitor had a self-resonant frequency of 24 point something megahertz, which would be terrible. And when in fact it really doesn't. It has a self-resonant frequency that may not be that high, but it certainly isn't 24 megahertz. Now let's look at the same circuit again with the 4170. The 4170 output being imported into SimSmith. We're going to plot L. We're going to sweep it, and we're going to see that the measured value right here appears to be inductive at frequencies above 24.66 megahertz, which is exactly what we saw with the 4170 software. And that's to be expected because this is exactly what we're looking at. This is just the data output from the 4170. Now we're going to put it through a piece of transmission line to undo that. And we see this. We see that it no longer is inductive, it's only capacitive. But this doesn't really show it very well. Let's look at the square chart for a moment. And I wrote a couple scripts here to plot the reactance as looking here to the left, and the reactance is looking here to the left. The reactance from here is the blue curve, L sub x, and we see that at frequencies above about 24 megahertz it becomes inductive, and that's what we saw in the 4170. And then when we compensate for it, it's the pink one. We're compensating for it with 1.42 inches of 0.95 velocity factor, 360 ohm transmission line. It's lossless. And that's pretty much exactly what we saw from the 4170. Now we're also going to plot the capacitance, and you can plot capacitance by, you know that x sub c is 1 over 2 pi fc, so c is 1 over 2 pi f x sub c, and that's exactly what this is plotting, but we get megahertz in terms of megahertz, not in terms of hertz, so we have to do a 1 times 10 to the 6th here, and since it's a negative value, we don't want to show capacitance as negative, we put a minus sign in front because the reactance is negative. And if we do that, we see the raw capacitance being what it was before. It started off value down here on 900 picofarads, and went up out of sight, and it came back down. It was inductive, which was unfortunate. After we compensate for it, we get this curve. It starts at around 900 picofarads. It stays close to 900 picofarads up through 50 megahertz or so, indicating that we compensated for it pretty well. This isn't the only way to compensate for that. We know that since it's a short piece of transmission line and it happens to be pretty much an open circuit on this side, this is going to look like an inductance. Let's see what we can do if we put an inductance in there and use that as our compensating mechanism. So we'll put a load generator block here, which will copy this load over to here. And let's just put just an inductor here. Now it needs to be a negative value inductor. Oops. And we need to look at let's look at what the effective capacitance would be with this inductor. Except this time it's going to be in the output of inductor L1. So we need L1 in here also. We don't need to redefine axis Y2 a second time. It wouldn't have hurt us because it was named the same thing as before. Now we should have an extra. We should have an extra plot, and we do. Now let's adjust the inductance value. Somewhere around 40, 45, 46 nanohenries, we can compensate for this for the leads just as well too. Anyways, both of these work. If you do that and you start to scan the circuit here, with this being compensated out, then you'll find out that you get what the true capacitor is. Now I also did some other scans of some different circuits shown here. Here was the capacitor, the 910 picofarad capacitor. I started off with the long leads. I cut them down to 0.4 inches. Then I made them as short as I thought I could reasonably make them. I put a little. Here's a 1,000 picofarad Mylar capacitor. Here's a 1,000 picofarad 0805 ceramic capacitor, and here's some little clip leads. So let's look at all of these. I guess we look at it with the 4170 software. It's probably just as easy as anything. So let's load a graph. The 4170 is not very multi-monitor friendly because it keeps bringing up this window on the other monitor. And let's start off with the 0805 ceramic capacitor. It is incredibly good. We see this. It's a different scale here now too, but here's what the reactance looks like. We see it never becoming inductive, and if we measure the capacitance of it, we see it stays around 1,000 picofarads, way up here, pretty nicely. Let's compare this to the Mylar capacitor. We're going to overlay a graph with, say, circles, and the Mylar capacitor is this one, and we see it actually becoming inductive. And I really believe it actually does become inductive somewhere in this frequency range. Mylar capacitors aren't particularly good as far as being super high frequency. Their claim to fame is they're very stable and that kind of stuff. So I would expect that. Let's see what the silver mica capacitor looks like. We'll overlay that graph with squares, and we'll do a silver mica capacitor mounted directly. And we see it really, when we have those kind of leads on it, we see it becoming inductive somewhere in the 70 megahertz region also. This is what you get. Now, you typically will not be using a 900 picofarad capacitor at 70 megahertz. You'll be using something of a lot smaller value. The reactance of the 900 picofarad capacitor up there is very, very small, but it does show it becoming inductive. We can also look at what we get here with these little clip leads. Let's just load that graph by itself. They're 2¼ inch long clip leads with little Mueller clips at the end, and we see it becoming inductive right away. Pretty much the same place as we saw with the other leads, although it should be a little bit worse. 23 megahertz. We can compensate for those, and we can compensate for those similarly to what we did before with line extension or anything else. And what you'll find out is these clip leads, if we move them out like this, they look like a certain inductance. We move them in like this, they look like a different inductance. And the value varies, but it doesn't vary a lot. Now let's do 3 scans, one with the clips being pretty close together, one with them being about 1.5 inches apart, one of them being about 2.75 inches apart. This piece of copper sheathing is 3 inches by 1.25 inches, and I'm assuming the inductance of this is pretty close to 0 compared to the leads. which I think is a pretty reasonable assumption. Anyways, let's see what we get. We're going to scan the narrow one first. And the narrow one shows an inductance of just about 50 nanohenries, as you can see right here. And it's pretty constant with frequency. 50 nanohenries for the narrow one. Now I have the clips in this position, and I'm going to rescan on top of this one with this being the configuration. And we would expect to see more inductance. And we're seeing inductance values from about 75, around 75 nanohenries. And now I'm going to move the clip leads out to the extreme ends and rescan it one more time. We should see more inductance still. We're starting to see a little bit of a slope on the inductance, which is due to an impending resonance somewhere out here in the future. But here we see inductances of 88. So the numbers run between 50 nanohenries and about 88 nanohenries for this set of conditions. And you could easily make yourself a little table and compensate for the amount of inductance you would have in these leads. And that would not get you a perfect answer, but it would get you certainly an adequate hobbyist type answer for many things that you want to measure. If you want to measure a balun that has some terminals that are wider spaced that you can't connect a coax connector to directly, that doesn't have a coax connector, you would need to put leads, or some kind of a component or something like that. The purpose of this video has been to try to give you some ideas that will help you be able to make better decisions when you're making measurements, and consequently your accuracy will improve. Like I said before, I could do a video on making the loads themselves, but I think for most people, the biggest weakness you have is not the instrument itself and not the open short loads, but how you actually use it. I may be wrong. Let me know what you think. And as usual, hope you enjoyed the video, and there'll be more to come.